Okay, so I'm a robotics guy, and I'm leading a project, Robotics, which I will tell you something about in a minute. It's on robot control, and we are starting a quite advanced kinematics dynamics part of this project. And I know Blender for about 3 years or so, and I think it's a very good occasion to exchange ideas and hopefully to share code in the future. So I will say a little bit about my background and also a little bit about where I see a potential for this project within the wider robotics community, commercial, industrial, as well as research. And then I have 4 topics I will go through into a little bit more detail, where the link between robotics and Blender is just very, very high, and where we can add some things to the project right now. So my background, a little PhD thesis which dealt, among other things, with advanced robot kinematics. And robot kinematics is the same thing as the computer animation, or the animation of computer images or creatures, animated devices. Currently, my research is on intelligent robot control, so we want to do more than just move around with the robots. We have sensors that sense the world, and where we can do intelligent things, between a lot of parentheses approach. Basically, the tools we're using there is real-time links, RTAI, and some Bayesian estimator libraries. Most of them are open source things we contribute to when we started. The main project is Oracles, which started 4 years ago. It's on the control of these devices. And we want to share that. So the rest of this talk is about the things we think we can share and we can give and take from Blender or through Blender. I'll give you a small example of what our Oracle software can do now. So you see here, the guy is holding the device. This is a tool with a couple of infrared LEDs, and this thing is 3D camera. It's interfaced with this controller. We use real-time internet to go to the robot controller, which is a PC running real-time Linux, and it's controlling these robots in real time. Okay. It's also a little bit commercial for Belgian beers. At this stage, they are more advanced and more control. Okay. Just to give you an idea. All these things do not have any visual interface yet. We don't have a graphical programming or visualization interface, and of course Blender will be a very good candidate to fill that gap. Not just for our project, but for a lot of other projects. Because when you have a situation in robotics, if you look at the industry, so the commercial vendors of robots and robot programming tools, you have a situation which is very comparable to the desktop, but even worse. So the lock-in in one single manufacturer, one single vendor is very, very high. So you buy a robot, you also buy a computer programming language for this robot, you buy this computer support, and you buy an IDE, you buy a graphical environment, all tied to one single vendor. So it's a very dramatic situation. That means that the progress of state-of-the-art in robotics in software is very, very good. In research, there's a different story. There are too many things there. There are a lot of open source projects, but the basic message there is there's no common platform. Everybody does its own OpenGL thing. There's no way to exchange things. All these things are poorly done, especially comparing to Blender. It's very, very poor quality. So I think that for all these things, Blender can be the common platform. Not just for the research team, but also for the industry. I've been talking to a lot of people in the robotics community, and they all say, okay, Blender is probably the common platform, but it's so difficult to use. A lot of things, reasons that robotics people are not using Blender at this moment. Anyway, there's a lot of interest. One of the things I will single out is armatures, because armatures is basically what we in robotics work with most of the time. We're not that much interested in how things look the fresh look around the armature if you're interested in the armatures. So this is one robot we modeled in Blender with an armature. This is a robot of the future. And if you know Blender very well, you know these things very well, you see that there's a problem there. And the fact that in real world, people do not use degrees of freedom as they are used in Blender. So Blender, armatures, and also the other similar programs, they use mostly spherical joints, 3 degrees of freedom joints. And you have to put constraints in the armature joints in order to give something which is used in the real world. So these are just rotational joints. All these things are rotational joints. So 26, 28, or 30 rotational joints. So having a much more flexible armature with all these vertical joints is not a good thing to have in robotics. So the good news, I start with the good news. I've been looking into the codes in detail, at least the kinematics code. The geometric code, it's very good. It's really very good. It doesn't have everything that we need, but it's it is very good.
Not bad.
Yeah. I mean, compared to what I know in robotics,
the rest is very good.
clean code, I was able to understand it a couple of days.
Our system itself is quite nice.
That's another thing. The code is clean. I don't say it's perfect and it's
We call it and
so I can recommend. So one of the things is in robotics we really need very good and prismatic joints as the basic building blocks. Why is this? Not because you cannot use spherical joints and put constraints there, but because if you use these very good and prismatic joints as building blocks, you can make the whole kinematics much more computationally efficient, much more computationally efficient. We're also interested in physically realistic simulation, not just things that look realistic, but that are physically realistic. And therefore, also in another area that we are starting to work in, that's the simulation of how humans work. So we want to simulate muscle activation and walking patterns for real humans. So biomechanical people are very interested there. So you need more advanced things that we have to be able to attach to joints or to motors in the armature. It's not all that difficult, but at this moment it's not there. And it's not easy to attach your own things into the armature structure. There's also a very poor infrastructure for redundancy. Redundancy is, you can move your hand in many different ways. So you have more motors, more degrees of freedom than you really need. So how do you solve this? I will explain a little bit more. This is the mathematical theory that has been developed in robotics, but also in computer animation, to solve these things. And this weighted series inverse, the weights are very important, because the weights you can link them physically to a physical concept like elasticity, mass, distance to joint limits, and so on. And we will also be...
The weight is like a physical construct. It's built in the armature structure.
Yeah.
So we don't add all these constraints to the quantity of storage.
Yeah, but you have to be able to fill out the specific properties. So it's very difficult. Now, I only know of writing code if you want to change the elasticity or the mass distribution. We've been looking at Python calls to do all these things, but we didn't find them. So if they are there, I apologize, but you should explain to me where to find. Also, there are constraints in Blender, but as you will see, you want more. So most of the real devices in the world, like humans or real animals, they do optimization. They do energy minimization as a constraint optimization problem, mathematically speaking. So Blender has already part of these things, but I think we can add much more. I will give a little bit more details in Python. Also, another thing is that you have a large family of different devices. So a classical industrial robot arm is very different from a humanoid robot. So they could have the same interface. So you move something from A to B, it could be the same interface. But the algorithms are quite different, or you can have much more optimized algorithms for each family. So it would be nice to have the same kind of interface, but be able to easily link different implementations in the same way.
What would be more efficient hardware?
So, for example, the robot I showed, or all industrial robots, they have inverse kinematics that you can calculate 1 million times a second, because the mechanical structure is such that the inverse kinematic is very, very simple. But if you have a general armature, you have a numerical inverse kinematics, which is much less efficient.
And also, is a representation and animation.
Well, a humanoid robot is a robot that looks like a human. The one that I showed, it's called a humanoid robot. So this structure can also be given efficient implementation, which is much more efficient than the general numerical approach, because it has some structural properties that allow you to make things more efficient. So there are a lot of categories for which efficient algorithms exist, and for which the general purpose numerical iterative algorithm is overkill.
This was a great role adding of complexity.
Well, that depends. I would call it adding of simplicity, but probably you mean the same thing. So,
attach the door in the car all the time and back to it. It also has to work, but it has to be more precise. So they want the door to be exactly on, and the robot doesn't have to bother about falling over. So
but this is more the control aspect. So for the kinematics, it doesn't matter too much. So being accurate is not just the kinematics. Because everything also has a control with the ground. That's another issue. So I'll give you an example of the simulation we did not in Blender for the time being. So here are constraints. You have a humanoid figure, and there's constraints. So one eye looks at the hand follows a certain object, and you have constraints in the posture of the body. So there are constraints to keep the center of gravity above the foot. There are constraints to keep the back as straight as possible. So there are a couple of constraints which are not hard constraints, they are soft constraints, so you can violate them. But you violate them in a physically realistic way. So also a human figure, we have elasticity in our muscles, not just passively but also actively. We optimize minimum the energy we spend in certain motions. So this motion is completely generated from one target that you move, and the hand follows the whole thing. And the rest, there are no keyframes in between. So this is in the inverse kinematics, and the weights here are defined by the mass. And I will show you the blue line is a constraint that you want the head to follow. So you can do something like this also in Blender now. You can track constraint, but this is not a hard constraint. It's not a set of rules that we do and values that we put. It's an optimization algorithm that is behind all this. Another thing I'm a little bit worried about, you never see real physical units if you work with Blender. You really need physical units to be available everywhere. So everything should be in meters and kilograms and so on. There are already some things. Yeah. Well, you have Blender units.
okay.
But what do you mean?
What kind of
I need millimeters and radians and all this. Especially also for the verse project that you're working with. If you want devices from different organs to work in the same world, their scales have to match. So I can draw something that looks very well, and I put it together with something that looks very well made by somebody else, and it can be the scale difference of 100.
That's why I think it's very shallow, because the unit itself doesn't change. You map the unit to something, you could understand to find the mass, the weight, stiffness, or dimensions of objects.
Yeah, but as soon as you model physics, then units are important. Because I say, okay, this is 10, and I need 10 kilograms. But in the US, they say, okay, this is 10, but this is 10 pounds.
Oh no, we don't do that.
But, as I but anyway, units should be a bit more visible, at least for people that want to have them. There are also, there's already a lot of physics in there. So we have ODE, which is very nice, but it's very complementary to what I explained here. So ODE is especially interesting if you have a lot of rigid bodies that interact, collide, and fall, and so on. The things I discussed about, they have much more efficient things for the dynamics than with ODE. So you can make a robot with ODE that will behave in a physically realistic way. It will be much less efficient to do than doing it the robotics way. Okay, this is something I said before. It's not a complaint for myself, but it's not No, I have nothing against choosing a certain interface, but the fact is that most software programs available in robotics have a different user interface. And so,
it's interesting to make write down what the perspective is, what the application are for robotics. I don't know what they want.
well, they don't know.
I think they're working on real robots. I have a computer for a real robot. But we want to simulate everything in a vertical department. And what is the purpose?
Well, different people will have different purposes. Personally, for me, I want to make simulations that transfer the results to the real world. Or the other way around, have something real going on and see it in the visualization. But other people will stick to virtual reality. And so, the roboticist doesn't exist. And the requirements from the roboticist or robotics world, there will not be in so don't worry about that. Okay, so if you generate motion based on constraints, then you can do it less keyframes. The easy way to do it, I will give you the mathematics in a moment, not too difficult, is if you have linear constraints on velocities, or similarly potential fields. Potential fields are force fields that attract parts of the robot to somewhere else, or to make the robot move around something. So you have a force field, for example. I don't want to touch this mic, and I can put a potential field here that pushes me away from the microphone. These are easy things to do. These are some things, animations we visualized in Blender but didn't calculate in Blender. So this is a motion specification of the robot where we have it do two things at the same time. So here we have a circular motion with a certain speed here, and we have another circular motion with a different speed and different radius here. These things are simulations of laser strands or Kelvin spots or whatever. That's not too important. So we specify the motion, the desired motion at this intersection point. We specify the desired motion at that intersection point, and that's all. All the rest follows immediately. You see the base is moving a little bit, so we didn't constrain the base. The motion of the whole robot falls on these two specifications. And from some weights that we put onto the robot part. For example, we wanted to stay away from similarities. We wanted to move most of its lighter joints instead of the heavier joints and so on. Here you see another one. When the robot moves to the door, the only specification we did is that the robot pushes against, so the door has a circular motion, that's all, and the rest follows automatically. So all these things can be done with linear constraints on velocity. So it's not too difficult to implement. Which is a little bit more difficult if you go one level up to acceleration. Basically, you go to dynamics. So these demos are at the kinematics level. just velocity specification. If you go to acceleration, then you get things that I showed before that you didn't know before. It can also be done. So all these things are done with weighted pseudo inverse of the Jacobian. That's what it's called in linear algebra. And the good news is, even for robots with 30, 50, even 100 degrees of freedom, these things can run in super real time if you code them efficiently. So if you take care of how you implement it. Not with the general approach that is now in Blender, but with a little bit more efficient ones. So the mathematics, very easy to explain very shortly. This is the Jacobian transformation. We have the velocities of your joints. We have a matrix that multiplies it into the twist, the velocity of the end effector. Yeah? So the end point of your empty at the end of your device, whatever it's called. This is in Blender also. Now, if you have more joints here than the 6 degrees of freedom you need there, you have a redundancy. That means you have null space. That means there's a set of velocities at the joints that give no motion at the end point. Yeah? So mathematically speaking, that's this. That means that you can derive the same result, you can get the same motion of the end point of your robot by a certain set of joint velocities, and you can add anything in between. So I can do this motion, I can do the same motion with my arm like this. Yeah? So while I'm doing this motion, I still have internal motion degrees here. So what does this allow you to do? You can add a set of linear constraints in velocities so that the Jacobian is extended to a square Jacobian that you can invert normally. This one is not a square one, so it's 6 by n, where n is the number of joints you have here. So you can extend it with linear constraints and then with a normal Jacobian that you can invert. That's one approach. The second approach is you go to a quadratic minimization problem. So you have somewhere a constraint on these velocities. Here I've written it in the form of kinetic energy. So this m is a mass. So here you have this 1/2 of mass times velocity squared as units of kinetic energy. You probably remember this from your physics classes. And this is the constraint that we put on this optimization. So this is the minimum. I want to spend minimum energy, minimum kinetic energy in doing something, but I still want to have my desired motion. So if you solve this can be done very efficiently, then you have the motion that I showed you before. So this is just one minimum kinetic energy, is one criteria. You can come up with all kinds of optimum optimization criteria. That's the minimum potential field. That means you have a lot of strings attached to your robot and you move to the equilibrium position of these strings. You can go to kinetic energy, then you have a mass distribution in there. So you can have a lot of these things. How do you solve it? This thing is solved in closed form in this way. So this is Jacobian, this is this mass matrix here, and this thing is called a weighted pseudo-inverse. It's often denoted like this. So this is not a good way to calculate. This is just an analytical solution. There are numerical techniques that do it much better. Still, this is a general numerical technique. For all the robot families, from a simple industrial robot to a human robot, you can do this, you can short circuit this. You can find more efficient algorithms that have the same result, which are much more efficient. Okay, I said most of these things already. So for this simulation, the weighting there was the mass matrix. This is one of the famous robots that you probably see from Japanese commercials. And every big company in Japan has their own humanoid robot. What they do is they program these devices in such a way that their motion looks like a human motion. So they capture the motion of a human and they play it back on these devices. Which is a stupid thing to do because it spends a lot of energy. It's too energy consuming because the mechanics, the physics of this robot are very different from the physics of a human. So if you apply this technique to these devices, they move very differently, but much more efficiently. So this device, this robot, it has a big Pentium CPU inside which consumes 150 watts. which is half of the energy consumption of the whole device. So these things can only work for 20 minutes, 30 minutes, and which is still a very good achievement. It's very nice development, but nevertheless there are some limits. So I have a set of, I think, 4 or 5 developments that we are going to do anyway within our project that I'm very interested to do together with people from the Blender project. So the armatures thing, as I explained, I think we can have maybe a bit more structure there. We have some categories, families of armatures, and GUI in which you can build these armatures more to what roboticists would like within Blender. Then this constraint optimization, the motion generation, the potential fields of via the pseudo universe. Another thing which is important for the real-time control is that we would like to focus on kinematics libraries that you can use in real time. The current one that's now in Blender uses TNT as a library. This library still often allocates memory during a process, so it allocates things on the heap, which is not very efficient for real time, but maybe that's a detail. So one alternative is to go for a library that uses standard expression-based linear algebra. This library doesn't exist, or there is a library that does this, but it doesn't have all the linear algebra that we need at this moment. Another thing we are very interested in is to interface, to use Blender as visualization of something that's going on in real time, in the real world. We have done this already. We have a Python script that communicates with our external controller and that just moves the robots in Blender around. But maybe the Verse project will do this for us in the near future. I missed the presentation on the Verse project. Maybe we can do this already. Because I've seen the specs, they have this kind of specification. We also have, I had a couple of students this summer that work on a chapter for the Blender documentation targeted to roboticists. If there is interest, it's somewhere on the web I can show you, and we're willing to do some more. Okay, so I come to my conclusions. Blender is a very exciting project for robotics people. Very exciting, but not enough people know about it, and even less people do something about it. So that's a job that I'm taking now in the robotics community to make more publicity for Blender. I think major contributions from robotics to Blender are in these 2 areas. So more advanced, faster, more generative mathematics, and physically realistic generation information. Much less keyframes and physically realistic. These 2 things are, there's no research anymore. These things are mature. Everybody knows how they work in robotics. It's a matter of implementing them, finding correct interfaces, finding correct decoupling of components and so on. But the development is done. What would we like to see in Blender? That's a much more flexible armature thing. Also, robotics is for 80% people that do mobile robots, so automatically running cars, and maybe some good car armatures would be very interesting there too. And some extensions at the GUI point, the functional point, and Python. Python is a very, it's a gem within Blender. So, but within Python currently you cannot access all the things that we would like to access. We're willing to contribute there, but we don't know very well how. Okay, I will stop here, and I think there will be some time for questions or remarks.
One of the first things I don't really understand the workflow. So most, 90% of what I'm reading here and the stuff I heard from you, I don't think it's any problem to have an animation of the things. But how does the move from your robotics background, how does the workflow look like? Because I know when animators do training, what I do. Yeah. But you do have to reality. You need to devise
That's one of the possible ways of doing it, yes. I think most of the people would be interested in this. But there's no single workflow that you can identify for this. So I only talked about things that I myself feel it's very doable to do this in short term, to integrate these things in Blender or use Blender earlier or whatever. So I learned the lesson, so my vision is much longer term in my head, but here I only presented the short term vision. But the workflow is much more difficult because this thing has not matured. There's no such thing as robotics people work with software environments in this way. So there are still 25 different approaches, so it's much less mature.
So that would be like a vertical lab to do, which you would use to construct elements, dynamic test setups,
to write programs graphically.
That's use it, or just use it. But there's no absolutely need for it to have a connection.
That would be perfect, of course, but I think that's longer term. But yeah, I mean, there's no
complex. I don't know how that works. Usually when I see a robot, I don't see a computer. That's always happening. And it's like, from little ship in it and you take it and it's not good. That was all there.
I think there is something else in that workflow. I think what a lot of people like to have is like to have this in Blender, multiple view on the same concepts. So, I mean, the robot itself is a physical view on the concepts, and in your simulation you have a virtual view, and you can learn from both views because you can get things, or in the virtual thing you can just cheat physics, and you can come into solutions that you don't come across when you just expand the physics. And the other thing, if you're in the virtual reality, you never know what the real thing is doing. I mean, so if you try to do football, it's a football robots. Complete strange things are happening.
So one of the things we in our intelligent robot research are very interested in is to use Blender to visualize what the intelligence in the robot software is currently thinking about. So if you have a vision camera or other kinds of sensors that mold the world in one way or another, it would be very nice to be able to visualize it in Blender. So to see what is the current view of the robot of the world. Now it's somewhere in the computer and you can see, okay, probably it's doing this or this, or we can check afterwards and go to the numbers and so on. But have a real-time visualization of what the robot perceives in the world in a graphical environment in Blender, that would be very, very good. So therefore you need this two-way communication. I think First can do this, or will be able to do this.
Aside from the Terminator.
Sorry?
Aside from the Terminator, to do with
yeah.
Now, this other aspect, not to solve all everything today, but what I was cast animators, really still alive. There's a reason for it, but artists, they want to have control over the motion. By putting things and moving things around and doing things smart, you get emotion with emotion and storytelling. So they're not interested in one construction solution that keeps makes things work.
Yeah,
and actually that's also a part of the hardware.
Yeah,
but it's interesting to find out how can a robotics arm the system help enhancing or making work and easier experimentation for the
So one thing is that if you have the normal natural motion is guided by physics for all real creatures. So in that way it can help. So you need less keyframes. You only need one. It's the one you're following. And the rest is generated automatically. Another thing which is very different between character animation and real world is we cannot put keyframes in the real world and change them such that the robot moves the way we would like in a world that we don't know. So in a world that you know perfectly, that's a viable thing to do. But in the real world, you can only do this to a limited extent. So there are different goals.
What would be very interesting approach is like to find out if you can get these both roles somehow connected. For example, when you have an animated answer, completely invalid, no physical talking to the door, usually that's not physical. There are always these narrow things in animation that think that's better or I want to improve that. And then by adding the simulation on top, you can make it look better.
For example,
possible, but you can combine or convert the kinematics into a dynamic situation. You solve it again and send it back as a normal kinematics. I think that would be one of the tools.
yeah, I think that's in the pipeline, and the large animation studios, they are already a long way along this path. But I still see, if I look at these animation, the special effects in many movies, I see errors in the dynamics. So a lot of dinosaurs, they seem to be able to jump from here to there without doing this. So that's the physics which is not
Yeah, I still think that more artists could profit from more realistic physics simulation, especially in real time, if they're interested more into doing games and using the gaming engine. Because there, for a game, the more you want it to be interactive and real-time calculated, the less predefined animations and keyframes you should use, because then you're just adding loop to loop and not really being fully interactive. And so I think that would be a good thing also for designers. Not that they, as you said, on one hand they'd like to explicitly tell the armature how to move exactly, and on the other hand, if you were trying to do a game with realistic looking animations, physically realistic looking animations, then they might really profit from these kind of development.
Yeah, absolutely. But you see it already in the animation studios. For example, large crowds. So the motion of this crowd is defined by moving one key figure, and all the rest follows in a potential field approach. So they are all connected with springs. They all have some individual liberty, but they follow the leader. So these things are very easy to program if you use some physical metaphors there. So if you move in group, mentally you're connected with little springs and dampers, and you follow the guide and the rest follows in natural motion. So you can specify the motion of one on the ground that all the rest will follow. So large crowds that you stream out of a football court or whatever. This is fluid dynamics. So there's a lot of physics that you can use for these kind of effects and that are being used.
So you were saying you can use physics as a metaphor. You can change the laws a little bit, but then you have to specify much less all those keyframes or all the specifics. So you have a metaphor for constraint-based manipulation.
Yeah. So the real constraints in the real world are physical, but not in the human world. The social world, the constraints are not physical. People tend not to stick very close to each other. So if you put more and more people in the room, the distribution will be more or less equal. There will be a minimum of some potential energy functions. Everywhere there you can use physics method. Okay, no more.
In the email about the exchange of the managers, I also proposed an idea to think of first adding on robot principle or entity, robot construction, creative because in all the weaknesses and problems, you saw yesterday 8 years ago.
Yeah.
People have a certain perspective of what it should do and how it can be improved. And maybe that roadmap is too complex to match what you do. I've seen the data data we have that it's so horrible and so scientific how it works. I think it's better to start that from scratch. To think of a much higher level arm system, where the bones and the joints have a much more advanced properties. But a lot of aspects of constraints are built in properties of arms. You don't have to add all the things, you have to do a lot of work to do what they call cast and rigging, building a cast and a lot of work. To make that into a very physical construction kit.
That's the building.
How do you construct the movement? Like getting the bones and putting them together and creating flash around it and stuff and kicking and that's what.
No, I agree with you, but
It's
also
going to case first to some people. Never.
it's not that big a step. It's a step, but
you can make it visual and it's very how the joint works. So instead of using the type in, this is a physical joint with a freedom of blah blah. I can display
that's the kind of building box we are thinking of. So a couple of these primitive things that you can connect, and every time you connect, some physical constraints are automatically configured, or you get the option to configure them. For example, the limits of the joints or the mass of a certain bone, things like this.
So it gives you a lot of freedom to start from scratch and take all the things you want, and you can move in a certain stage back to the animation side. Because I think you first want to fulfill a lot of requirements, like this weight that introduces coming to the block. Having a really good physics in it, and introducing a lot of speed.
The way we do it now, we have a robot, and we just have a robot with 6 links. Additional one, we have 6 different bodies, and we have a Python script that just puts these 6 bodies as if they were connected, but we do all the calculations in external program. So it's something simple. But we'd like to move things.
The other way is still possible to do. I would also now on RC, on the mechanism, the question was to look at how we can clean up the make it ready for the next one.
So within the Orbis project, we have a couple of design suggestions there, because we are going to do this anyway. So I would like to do it with Blender, but we're going to do it anyway.
And then a lot of feedback, of course, from the artist. What is it that you make, and what would you like to see that makes it easier for you to control the character? That's how easy it is in things like you expand that with the path and strike and still it's different. Right? So if you would define like what you saw with the little ball and you move from square for the hand, maybe you can just foot function on the floor for the path. And the guy has to move over the path with the person.
It would also be cool if you could marry different animation with overall constraints in kind of a smooth way. But you can't. The stride run on a path is actually, as I said, it's a primitive way of doing it, and it is primitive, and it doesn't really offer. You have 2 variables to see if you can get it right, they match, but it's what you want to have in another way to do it. But I've seen other systems, and I wish you use those programs more to really comment on them, because I only know from demos what people do when they're trying to make programs up. But exercise, for example, has much better ways of doing path walking type problem. And it's also using a walk cycle that someone's building that has a character. It's tweakable throughout the block, but they can define carrying how things are. And while the thing is walking and it's achieving this walk cycle, you can actually move the paths around, and the thing reacts dynamically, beautifully. And I don't know how to do this.
Yeah, I know. I mean, that's the way these humanoid robots walk. Eh?
Yeah, it's really
So there's a control loop there, which is a little bit more complex than the kinematics and dynamics, but this is also known technology.
They do make an evaluation of how, for example, something eyes or motion goes from kind of or what's popular how they give access to artists and
Well, I have been looking at lots of web pages, and I didn't find the technology that they use. Maybe I didn't look far enough, but no, I don't know.
They usually hide it.
I guess
You have to have software and hide it yourself, and then you might not know what they use.
probably.
But they, this design phase is important for an interface. You know, you have to do the talk this morning about back and forth and how to make it. But that's very important to try to build it works. The metaphor, the little things you can understand. The physical part is how to do the elements and how to combine them in construction. These kind of decisions are difficult to find.
Yeah, we have some ideas, or the robotics community has some ideas. But walking is reasonably well understood now. Okay, thank you.